Okay, so let's revisit what we did earlier and connect it to the proof that we wanted to do, which is that there is no bijection from Z plus to R. Now, what we did earlier was we said Alice had a box and she had to show that it does not contain a white paper with a blue dot. And so in that case, the box could have contained some white papers with the yellow dots, blue papers, yellow papers, whatever. Now, here we want to say that the box contains all functions from Z plus to R. Now, there are a lot of functions from Z plus to R. We could have a function like fx is equal to x. So that will map 1 to 1, 2 to 2, 3 to 3, etc. I could have f of x to be square root of x. In that case, 1 will map to 1, 2 will map to square root of 2, 3 will map to square root of 3, and so on. So inherently this box is quite big. In fact, we can easily show that this box is infinite. Now, what we want to do is Alice wants to prove to Bob that this box does not contain a bijection from Z plus to R. Remember, there are a lot of functions that this box contains. As I said, fx is equal to x, fx is equal to square root of x. The point is, Alice wants to show that all these functions are not bijections. Now, continuing from the earlier example, what we are going to do is, before we were saying if Bob found a white paper with a blue dot, he wins, otherwise Alice wins. Now here we are going to change that argument to say if Bob finds a function that is a bijection, then Bob wins, otherwise Alice wins. We want to show that Alice will always win, and essentially that means when Bob finds a function, Alice has to argue that this function is not a bijection. It turns out that really what we care about is that the function is not an onto function, because we can clearly create one-to-one functions from C plus to R. It's the onto that is going to get us in trouble. Now, if Alice needs to show that the function is not onto, what does it mean? That means Alice has to look at the function. So if this is a function from C plus to R, then she needs to find something over here such that nothing is mapping to this particular entry. To show that the function is not onto, I need to find some element in this set R, and I have to show that 1 doesn't map to it, 2 doesn't map to it, 3 doesn't map to it, and so on and so forth. Let's recall how the game is played one more time. Alice has a box with all functions from C plus to R. Bob picks any function from this box. Now we will revisit what it means on the next slide. Alice's job is to show that the function is not onto. We will revisit what it means in a couple of slides. If Alice shows this, she wins. If Alice shows that the function is not onto, she wins. Otherwise, Bob wins. And we want to argue that Alice will always win. So let's focus on what these two parts mean. What does it mean that Bob picks a function? So before it was choosing a paper from a box, that was easy. So now we need to be clear about what it means that Bob picks a function. So we'll look at that, and then we'll look at what it means for Alice to show that it's not onto. So Bob picks a function from the box. What does it mean? That means Bob has to say what the function f looks like. What is the function f? The function f is from C plus to R. So Bob has to identify what 1 maps to. So 1 maps to f of 1, 2 maps to f of 2, 3 maps to f of 3, and so on and so forth. Remember, the table is infinite. We're just writing a few entries in the table. But Bob has to identify this entire function, and then Alice goes to go ahead and show that it is not on 2. Now, what does it mean that Alice has to show that the function is not on 2? Essentially, that means Alice has to find a value, and the property that we want is that this value is not equal to f of 1, is not equal to f of 2, not equal to f of 3, not equal to f of 4, etc. So Alice's job is to find a value that is missing in this table. Remember, Alice gets to see what Bob is giving. So Alice gets to see what the function f looks like before she has to find the missing value. Okay. So how does Alice find the missing value? So she looks at the function f and creates a real number. This real number is going to be of this form. It's going to be a number from 0 to 1, so that's why I'm writing this as 0 point something. And then there are digits r1, r2, r3. These digits are infinitely long. She has to find all those digits. And her argument is going to be that this function f does not have any integer mapping to the value n. So let's recall what R1, R2 is. So R1 is the first digit in the number. That means it has the value 1/10. R2 is the second digit. That means the weight is 100th, and so on. She's going to choose R1 in such a way that M will not be same as F1. She's going to choose R2 in a way that will guarantee that M is not the same as F2. She's going to choose R3 in a way such that M will not be equal to F3, and so on and so forth. Remember, Alice's job is to find a missing number. So all that she has to do is she has to find these digits such that R1 will guarantee that the number is not the same as F1, R2 will guarantee that it's not the same as F2, and so on and so forth. So let's focus on how Alice finds the missing value. So she looks at the function and she looks at each value of f1 as some kind of a decimal expansion. So let's say we have f of 1 is 0.5. So I'm going to write this as 0.5 followed by as many zeros as I need. Square root of 3. So f of 2 is square root of 3, which I have written a few of these digits down. F of 3 is pi, so it's going to be something like that. F of 4 is 1/3. So that's going to be 0.3333 and so on. F of 5 is square root of 2. The way Alice finds the number is she looks at the first digit of f1. So in this case, the first digit of f1 is 5. The second, then she looks at the second digit of f2. She looks at the third digit of f3, fourth digit of f4, and so on and so forth. This is the rule she follows. If this digit is 3, she chooses 4. If this digit is not 3, she chooses 3. It's kind of like a kid doing exactly opposite of what has been told to them. If you see 3, make sure you don't choose 3. If you see something that's other than 3, choose 3. There's nothing specific about 3 or 4 per se. You could have played this game between 2 and 5, 3 and 7. There is a particular reason I don't want Alice to choose the numbers haphazardly, that is, I don't want her to just say if it is 3, she chooses something other than 3. The reason for that is a little bit complex, so I don't want to get into it. But that's basically what's going on. Alice, if she sees a 3, she chooses 4. If she sees anything other than 3, she chooses 3. Now, what I want to observe is this number that Alice has chosen. It cannot be the same as the first one. Why? Because this first number is 5. This first number is 3. If two numbers differ in one digit, they are two different. So let's focus on the number that Alice chose. It can't be the same as F1 because it differs in the first digit. It can't be the same as F2 because it differs in the second digit, and so on. That means it's a number that is not F1, F2, F3, F4, or any of the things that are mapped to by F, and that means that this number is not equal to f of n for any n, and that just means that the function is not onto. So let's review. Alice has a box of functions from z plus to r. Bob chooses any function. Alice wins if she can show the function is not onto. Alice always wins, once again, and I have told you, I'll say this many times. She always wins. She doesn't almost always win because that's not the same thing. And because Alice always wins, that means she is able to show that the function is not onto. And that means whatever function Bob chooses is not onto. And that means there is no onto function from z plus to r. And also it means that there is no bijection from z plus to r. So this is what it means that the set of real numbers is uncountable. Now I want to get into a little bit of philosophy here if you would like. There are some people who try to use this as like R is a bigger infinity than Z. At some level, they're absolutely right. Some people have strong objections to the idea that how can you have levels of infinity? Infinity is already infinity. How can I say one infinity is bigger than another infinity? If it is bothering you that much, I want you to focus on just the result that we have, which is there is no bijection from z plus to r. There is no bijection from integers to reals. That is the key that we want to get out of this module. A few more things to talk about. If we have two sets A and B that are countable, then A union B is countable. And the way we can do that is basically if I have a set A that is countable, that means I have a mapping from Z plus to A. So that means there is something that maps to 1, something that maps to 2, and so on. We have a similar function for B. So if I want to create a mapping for A union B, well, I just take the odd numbers mapped to the elements in A, but they skip an element at a time. And even numbers mapped to the elements of B. If I have a subset of a countable set, that is going to be countable as well. If A is uncountable and I show that A is a subset of B, that means B is bigger, that means B is going to be uncountable as well. The power set of Z plus, which is set of all subsets of Z plus, is uncountable. Now there are a lot of other applications of this work as well. We can say that a function is computable if there exists a computer program that will find the value of that function. If the function is not computable, that means that there is no program that can find the value of that function. There are uncomputable functions. This is one of the things that we will show in CSE 460. Now, the way we can show that is by basically showing that for every real number I can find a function, but for every program I can find an integer. What that means is number of functions that we have are about the same size as the number of real numbers that I have. But the number of programs that I have is much smaller, which is comparable to integers. Now both are infinite, but there is no one-to-one mapping from z plus to r, and that means, sorry, there is no onto mapping from z plus to r, and that means that there are going to be some functions that no program is going to be able to compute. We call these functions as uncomputable functions. We have reached the end of the module. I would like you to do the review quiz at this point. Note that this topic is somewhat challenging, so be sure to go over it one more time. Be sure to see that you have understood the proof of real numbers being uncountable and the fact that rationals are countable. That is something that will be important going forward.